Good afternoon. First of all, thank you very much to the organizers to allow me to speak with you. Yes, I will be speaking about the numerical simulations of long Gervais jets, launching in the center of collapsing massive stars. I am working here in Warsaw in the group of Professor Janiuk. Let me start with this slide in which I am showing the emission of long Gervais, and this paper is special because it's showing the emission at different times at different components of the ejection coming from the jet and the cocoon and the supernova. So this slide is a motivation that it's important to study to large scales every component ejecting from these massive stars because of many of those components have an implication in the emission at very late times. So yes, here we have been saying amazing simulations of explosions coming from the center of these massive stars. But let me say that the computational domain of these studies covers the center of the star, many of them. And our interest is what happens beyond of the stellar envelope and until the scales of 10 to 13, 10 to 16 centimeters, which is the typical scales in which where the jets are doing emission. The long Gervais, as you know, has a multi-scale problem, and one single run is not enough. It's technically difficult to run in only one single run the complete evolution of the jet, because we need to evolve at least 6 or 11 orders of magnitude in which the jet has to interact with the progenitor star and the external environment. But yes, we know a lot of details of Gervais dynamics, but the method that we have been using for studying jets is not properly launching from the center of the stars. We usually assume that the central region is, the jet is already crossed the central part of a star, and usually the jet is injected by hand and explored by changing the parameters, such as luminosities, jet opening angles, and injection times. Here I want to show some beautiful examples about how we have been characterizing the jet injection and in some way to some connection with the central engine activity. For example, here usually the jets are imposed with a history luminosity which is changing like a step function, which is turning on, turning off, and in order to produce these working surfaces, which in the future will be colliding when it starts to decelerate with the external medium. Every of those start to collide between them and energize the shock front and produce the high variability in the prompt emission of the jet. But another important point is that the jet morphology, let's say the cocoon, change the morphology depending on which component of the energy is dominated. If the thermal energy dominates, we have more extended cocoons, and if the kinetic energy dominates, the jets are more slim. And other important ingredient is the magnetization of the jet, because it's necessary for collimate the jet and drilling efficiently the stars. Or otherwise, if the magnetization is not enough, we can produce failed jets, which are of interest as well as a non-symmetric transients. And a combination of all of those elements are important in addition with the structure of the jet. And the jet coming from the central engine has some distribution of velocity and energies, and also could be interacting now with the supernova ejection. And all of those interactions could change the final structure of the jet, which is in turn important for to estimate the late emission of the jet. So here we study different structures of a jet, but we impose by hand this structure. Just as a summary of this kind of studies, it has been interesting, no? See how the initial conditions are very sensitive. For example, no, if we change the total energy, the jet opening angle, we can produce, for example, not successful jets, or not relativistic jets, but also it breaks the star. And also we have been imposing supernovas by hand, but not, again, the imposition is as a thermal bomb by hand. But now, yes, we want to connect all of these ideas just with the central engine activity, no? And another list of elements we put here that we are interested on that because it has connection, no, with observation, no? Which is the luminosity versus time, the distribution of velocities, variability, the mean lifetime of the progenitor, jet opening angles, and the final structure of the jet. So for this study, I will present the launching from accretion process. For that, we assume a fast spinning black hole imposed with Acker metric, an angular momentum distribution which goes as sin square, and a magnetic field. We perform simulations with different magnetic fields, magnetic field strengths. And well, yes, those are our initial conditions. We test 3 different progenitors, one produced by MESA, and the second one corresponds to model 16Ti and 12Th, which are Wolf-Rayet stars evolved by Huxley-Heger. But we choose such progenitors because are frequently discussed in the literature. And also we impose a magnetic field potential, dipole-like. And our simulations are so far 2.5 dimensions, just because, you know, they are computational expensive, but we are also now running in 3D. But as a first study, we want to see generate the jet from the central engine. The material starts falling and accreting around the black hole. The jet is launched by Blandford-Snarek mechanism. Here, the jet is successfully crossing the most dense part of the star and evolve. Yes, we have been running by 500,000 gravitational times, which correspond roughly 7 seconds of evolution. The jet breaks the star. We have central engine activity here. So the matter state is dominated here. We have variability. The jet is continuously injected, and we have here structures as working surface here. The cocoon start to engulf the star. Here I want to mention briefly the effect of the magnetization, because we explore different magnetic field strengths. Here is the sigma parameter, and well, we decrease starting from 10 to 14 Gauss, 10 to 13, 10 to 12. We decrease the magnetic field. Just for the effect here is we change the geometry of the magnetic field. In the center we have parallel lines, and well, and here is we have different progenitors. We have been exploring what is the final structure of the jet. The magnetization clearly has an effect in the structure of the jet. This is a two-side structure, have a very collimated core and less collimated jet wings, and this structure is disappearing while you have decreasing the magnetic field. You were asking, I think, about the one side jet launching. When we decrease the magnetic field, we got some jet which is only launched in one direction, and a cylindrical shaped jet. If you start with parallel lines in the core and more turbulent jet with the Wolf-Rayet stars. We have, well, in general, we were interested in high magnetized, weakly magnetized jets and non-magnetized models, just for, yes, thank you, check which conditions can break the stars. Of course, as you know, for example, we have the curiosity if just only the wind powered by just only accretion can break a star, but of course not. We need a thermal source here. But what was interesting, see the limit. No, when the winds coming from the accretion disk can support the jet, the shock front of this strong wind. Here is stopped, for example, and also the jet opening angle is important. Sometimes in some works are measured at the end of the simulation by the criteria of how magnetized is the jet. The criterion is the sigma greater than 1, and it can determine the jet opening angle, the final jet opening angle. But also there is something, no. The energy at the end of the evolution, the energy component that dominates is the kinetic energy, and can check as well a criteria by velocity, which change. No, the jet opening angle could change as in some simulations increase 2 times the final jet opening angle. Here I am showing just some usual diagnosis. The accretion rates, the magnetization has decreased as a power law. The range of the luminosities that we have been obtaining is between 10 to 50, 10 to 53, which are still high. And just let me this is one of the last slides. Show how what is the most important element of this study, or which is the most the element that produces the most important consequence is of course the structure of the progenitor. Our MESA progenitor, the jets that propagate inside of the MESA progenitor finish with the components of the energy are the magnetic, thermal, and kinetic are in the same order of magnitude. But in the other models, the Wolf-Rayet models, the kinetic energy dominates. And also, we made radial light curves for starting from, well, once you know the structure of the jet, you can estimate the afterglow emission by a self-similar Whelan-Fournier solution analytically, and we can see some difference, no, between the models. Well, I want to summarize our results. Well, the structure of the progenitor, as I mentioned, is the most important element of this study. The luminosities are in a range of 10 to 10 to 53, and we obtain different shock breakouts, but also it is affected by the progenitor star, and also, well, we change the magnetic field strength and the topology, and it modify what is the jet opening angle, and it successfully can break or not the star. Thank you very much for your attention. But also we have what extra thing, what if you have curious about gravitational waves. Well, so far.
Thank you, Gerardo.
Thank you.
Questions?
Two questions in parts. The first is thank you very much for the presentation in continuation of what was shown before. The question I had, the first question is the Lorentz factors. I may have missed it. Did you say anything about the Lorentz factors of your jets?
Yes. Well, we got the values about well, this is a map of for velocity, but what dominates in this plot the Lorentz factor. We have around 500. No,
Okay,
the
so
terminal Lorentz factor is, but in the local frame is tens, no? Because the limitation of the simulation, but the asymptotic Lorentz factor is
because of a floor density. You have to assume.
Exactly. Yeah.
So you get
500 is the terminal Lorentz factor.
You get meta carried in the jet. And the second question I had was about your final statement that the magnetic field configuration affects the opening angle.
Yes.
As far as I understood from what you said, is that to some extent you simulate consistently the infall and the jet launching. So when you say magnetic field configuration, you impose an initial field structure, and that has a final impact. So can you tell us about the assumptions which you used and the outcome, the corresponding correlation?
Yes, well, just for the magnetic field, we impose as a magnetic potential. Yes, the field component only. Just it's a dipole, like, and the other one is a combination of these. We use the same as Ori Gottlieb, which is in the center of a star. In the core is parallel lines at a set direction, and outside is a dipole.
Hello, thank you so much for the presentation. I was wondering, in one of your simulations where you show like different scales of the columnated jets kind of pushing through the layers of the star, once it reached the star's surface, it seemed like the outer layers of the star kept pulling up with it, and the jet seemed to get wider and wider. Does the gamma ray burst blow the star completely apart, or does it just shoot out a significant amount of mass and then the rest collapses inward to form the black hole?
Well, this question is a paper. But yeah. Well, I think you can break the whole star and eject all material, but part of everything is happening. You know, things are creating. We have fallback and ejections. But I don't know.
Further questions? So I wanted to ask you about the variability of the Lorentz factor. Like, how much does it vary? And in conjunction with a relatively high magnetization, let's say, you think how viable would be an internal shock scenario for the prompt emission? Because that's usually requires relatively low magnetizations, but is the variability of the Lorentz factor in principle strong enough to provide enough an argument of colliding shells than accelerated particles?
Yes, I don't have here the plot for the variability, but yes, the answer is yes. We have yes oscillations in the Lorentz factor along the set direction.
Okay.
You are asking about the delta T.
Right, and also the contrast of different shells at different velocities that, in principle,
yes. Well,
shock
here I think here in this video we can see in this structure roughly we can see some shells in this part.
I'm asking also because people like Ori Gottlieb sort of don't believe that this is actually a viable mechanism because they don't see enough variability in the Lorentz factor, and I was wondering if you see it something similar as it does, or maybe something that deviates. Okay. For the questions? If not, let's thank Gerardo again.
Thank you.